Okay, let's start. Good morning. So this week, again, we're going to keep talking a little bit more about vector spaces, but instead of focusing on the algebra aspect, matrices and stuff, we're going to switch to the geometry aspect. That means that we're going to introduce certain new structures on a vector space, things like inner products, norms, and stuff like that. And ultimately, we're going to have something called a metric as well, or a distance function. And then we're going to spend next week and the week after focusing on metric spaces. So this distance, so the structure given by this metric, by this distance function. But before that, I had promised you that I was going to talk about this, how to approach statements in this class. And then we were discussing this idea of this classification of finite dimensional vector spaces. I had mentioned how to prove the first part. I want to give you a couple ideas as to how to prove the second part. And likewise, for the so-called rank-nullity theorem, which I'm going to remind you again, I would like to at least give you some ideas. But before all that, let's first discuss this. And this is also included in the specification document for the first problem set. And even though I wrote these 4 items in this order, this is not in any particular order, really, because somehow mental processes associated to doing math is rather complicated. So maybe I should say in no particular order. So in the problem sets and exams, this is what you're going to be responsible for, right? Like I'm going to grade the proofs, the alleged proofs that you're writing, or counterproofs. But somehow, and this class is mostly about understanding, being able to write things rigorously, but that is not all there is to sort of higher math, let's say. And so I would say that first of all, it's important to be able to distinguish whether or not a certain statement is even true, right? And now, how do you determine that something is true or false? This is complicated to answer. Part of it is intuition, right? Like, I would say that it's hard to imagine that a mathematician sort of looks at statements and needs to sort of try to prove or disprove every single one of them before being able to say it is true or false, right? You need to have some idea. It might be false or it might be with some probability, but I would really suggest that whenever you see a statement, maybe in the problem sets, whatever, try to guess. How do you feel about it? Is it, you think, correct or no? And the next comes building a case. This could be about, this could be coming up with examples, trying to prove it, see if the proof actually goes through. Because sometimes there's a statement, and once you sort of open up the definitions and start writing the proof, there is nothing stopping you, and that basically gives you the proof. But sometimes you feel like a statement is correct, and then you start proving it, and then at some stage you get stuck. Now, maybe the reason you get stuck is that you don't know what to do afterwards, but maybe there's something fundamental wrong in what you're trying to do. That is to say, maybe the statement is in fact false. And there are other situations too, of course. Like maybe you want to sort of do sort of like simple calculations, or maybe graph it. I don't know, simple examples. And related to this too, you're going to realize, probably you started realizing, in this class, as opposed to sort of earlier classes in math that you've taken, coming up with examples is really your responsibility. I will try to do my best, and whenever I feel like examples are really needed, I'm going to sort of spend time on examples. But as time goes by, I'm going to give you less and less examples, and it's going to be just an abstract statement, something like this, for instance. It's going to be your job to come up with examples and counterexamples to basically try to understand what is being said. That is one of the big differences between lower level math and higher level math, right? In lower level math, you don't really worry that much about definitions. You give a bunch of examples and you hope that the student sort of figures out how things are supposed to work. In higher math, somehow you focus more on the definitions and the abstract statements and stuff, and it becomes a student's responsibility to sort of have at it, right? So the prod the definitions using examples or trying to come up with examples and so on. Next, of course, proving. And then once you prove a statement or disprove a statement, maybe I should say disprove as well. This is the next stage, perturbing the statement. And by this I mean something of the following form. So let's say that the statement you were given was of the form P implies Q. So if you assume P, then it follows that Q, the other statement, is also correct. By perturbing the statement, I mean something like this, perhaps. Let's say that there's another statement, P underscore, let's say, that is weaker than P. That is to say, it's another statement that P implies. Can you still prove Q assuming this weaker statement? Or you can say, oh, maybe there's a statement stronger than Q. Can you perhaps, assuming the same P, prove something stronger? Often perturbations are not this simple. Often what happens is that there's some sort of trade-off. If you're trying to prove something stronger, you end up needing to sort of maybe weaken the hypotheses in certain ways and strengthen them in some other ways. But this is all about this, what I mean by perturbation. And as time goes by, you're going to sort of have a better idea, I hope. So in a sense, math never ends, right? So things that things that we can prove or we might be interested in proving, they never end. And I think this last stage is going to perhaps help you get some sense as to how people come up with new things to prove. Because an outsider often thinks that there is nothing new to prove in math. But that is almost never the case. We have more problems than ever. OK, so that's all I wanted to say about how to approach statements in this class. Any questions about any of these? And hopefully this will be helpful for you as well in the exams, for instance, because one thing that could happen is that I might give you a statement. Maybe it is a false statement, in fact, in the problem set. And in the exam, I give you the correct version of the statement. So if you only thought about the false version of the statement and show that it is that statement that was given in the problem set was indeed false, then it might be harder to execute, let's say, during the exam. But in your free time, when you're sort of preparing, this is sort of like one way of sort of getting ready. OK, so that's that. Classification of finite dimensional vector spaces. The first part I had mentioned how to prove. I'm going to not repeat it. Let's think about how to prove the second part. It's this idea that if I have two vector spaces that are finite dimensional, this abbreviation means that, finite dimensional. If V and W are finite dimensional, then they are isomorphic as vector spaces. That is to say, there's an invertible linear transformation from one to the other one, if and only if this non-negative integer dimension is the same for both of them. Okay, so this is an if and only if. So it's a statement about equivalence. So it has two sides, right? You need to first assume that this is correct, and then show this. And then you need to assume that this is correct and show this. So I'm not going to prove this. I'm going to leave it to you. So assuming that V is isomorphic to W, I look at the definition of what it means for vector spaces to be isomorphic. It says that there's an isomorphism, right? That's what the definition is. Say phi from V to W is an isomorphism, is a linear isomorphism. I know that V is finite dimensional. Let's take a basis. Say beta, which is a tuple of vectors, beta 1 to beta n. So each beta I is one vector in V. And any vector in V can be written as a unique linear combination of these beta i's. And in particular here, n of course is the dimension. It's the number of vectors in beta. So let me remind you, this n is the dimension of E. Well, what you can do is you can push this basis of V to W using phi. So this I'm going to leave to you. Then I might write phi of beta consisting of the tuples of the images of these beta i's. Phi of beta 1, phi of beta n. Each of these is a vector in W. So this is a tuple of vectors in W. The claim is that this is a basis for W. Of course, there are exactly n vectors again, which means that the dimension of W has to be n also. Okay. In matrix language, what does this mean? It means that if I have an invertible, in particular square matrix, its columns are linearly independent. In matrix language, that's what this amounts to. Any questions? Okay. How about the backwards direction? Well, if I have two vector spaces with the same dimension, let me continue here. That means that I have one basis, beta, for V, and another basis, gamma, for W, and they have to contain the same number of vectors. Now, I want to show that V is isomorphic to W. Again, looking at the definition, that means that I need to display one linear isomorphism from V to W, or vice versa. It doesn't really matter. But one way to define it, a linear transformation from V to W, is to say, OK, so let phi take beta I to gamma I. For any I, phi of beta I equals gamma I. Then all you need to show is that phi is an invertible linear transformation, which concludes the proof. So maybe I should be clear here. Formalize these ideas, this argument exercise. This is the outline, so to speak. There's a couple details that I want you to fill out. If you're not familiar with these ideas, it's a very instructive exercise. Any questions about anything? And again, this is not the main topic of this class. And in the textbook, even though the textbook uses linear algebra quite extensively, that's the name of the game in multivariable calculus, I think it's not a major problem if you decide to take this linear algebra stuff as sort of like a black box and assume that these statements are correct. So there are other classes where this is the main topic. So the other theorem that we had mentioned was this fundamental theorem of linear algebra. In other words, this rank-nullity theorem that said that if you have a linear transformation between finite dimensional vector spaces, then the dimension of the input space equals the nullity plus the rank of the transformation. So rank-nullity, or the fundamental theorem of linear algebra. Finite dimensional vector spaces, and let L be a linear transformation from V to W. Then the dimension of V equals nullity of L, dimension of the kernel, okay, plus rank, dimension of the image. In terms of vector, in terms of matrix language, this says that if I have a matrix L, dimension of V is going to be the number of columns, rank is going to be the number of pivots once you do the row reduction, and nullity is going to be the rest, essentially. And so how do you prove this? Maybe I should ask you, any guesses as to how to tackle this theorem in this abstract situation? In my estimation, there's a trick here that takes a while to get accustomed to. And the trick is that somehow, even in this abstract situation, insofar as your spaces are finite dimensional, you can always reduce things to the Euclidean case, to the Rn case. In practice, this means the following. If I have a subspace, I can just come up with a basis for it. This is not an algorithm in the sense of computer science. But still, what you can say is, OK, so the nullity of L is supposed to be the dimension of the kernel. Let's say that the nullity of L is P. So let's say this is P. Let's say this is Q. Let's say this is N. N equals P plus Q. I just store these variables into integers, into letters. So P equals nullity of L, which is by definition the dimension of the kernel. Null space, right? If the dimension of the kernel of L is P, that means that there are P linearly independent vectors that spans the whole kernel. So Now what you can do is you can adjoin to this tuple of vectors a bunch of vectors to get a basis for V. Okay, so this is the tricky part. One can argue that one can do this, but I'm not going to write it down. It's rather abstract, perhaps, if it is not convincing to you when you hear it. Extend beta to a basis, let's say beta hat I added n minus p, that is to say, q more vectors in such a way that, again, this tuple is linearly independent, and now they span the whole V. We call that the null space, kernel of a linear transformation, is a subspace of V. Now the idea is to verify that if I were to take these added vectors and if I were to push them to W using L, the image vectors are going to be a basis. They're going to constitute a basis for the image. Then so these vectors beta 1 to beta p, of course, if I were to apply L to them, that's still valid, but they're going to just become the zero vector, which means that I cannot include them in the basis. But the remainder, which I know is not in the kernel, I know that none of these is the zero vector, I claim they're in fact linearly independent and they span the whole image column space. And so there are exactly n minus p vectors here, that is to say q vectors, which means that the rank has to be q, which is by definition n minus p. Again, I'm going to leave it to you to formalize. Questions, comments? Okay, let's move on. I think we did enough abstract, algebraic stuff. Let's start introducing geometry. Now, it turns out that somehow the way you introduce geometry to this business, this context of linear algebra or vector spaces, is by introducing certain functions whose outputs are real numbers. And under certain, so if you assume certain axioms, these functions model things like angle or magnitude, things like this. So we're going to have three things. One of them is called the inner product. So you're familiar with this, perhaps under the name of dot product. Something like this. it will be a function that takes two vectors and gives you back some number. Approximately, of course, you're probably familiar with this idea, the dot product of two vectors should be basically the angle between them, up to some constants. The second is what is called norm. This is a function that takes a single vector and produces a non-negative number. So this is approximately something like magnitude. So if vectors are supposed to be velocities, so both direction and size, norm of the vector should be something like speed, so magnitude. Maybe I should write these as well. Angle. This is angle information, to say the least. Magnitude. And then the final type of function we're going to look at is what is called a distance function, or metric. That is, in fact, defined not only on vector spaces, but an arbitrary set. We're going to spend 2 weeks on this idea. Takes 2 points and gives you again a non-negative number, which is supposed to be the distance between these 2 points. Okay. Confusingly, often in applications, this too is called the metric, because somehow it turns out that any inner product induces a norm, any norm induces a metric in this sense, but not vice versa necessarily. And so there are a couple of axioms, of course. Let me think how I want to do this. OK. Let's start with the middle part. That's, I think, the most useful for our context, for our situation. Let's let V to be a vector space. A norm on V is a function like this. Is a function this notation is supposed to mean that this is the general shape of the function and the argument you put inside, something like an absolute value if you want, such that well, if it is supposed to model magnitude of vectors, certainly the first thing should be that if the norm of a vector is 0, that vector has to be 0, and vice versa. For any v in B, the norm of V equals 0 if and only if V itself is 0. OK. Second, I want to say something about how scaling a vector by a number changes the magnitude. Well, of course, if I were to scale whatever vector I have by 5, the magnitude should multiply by 5. This is what is called the homogeneity property. For any C scalar, for any V vector, the norm of V scaled by C should be C in absolute value times the norm of V. Now, some people use different notation for the absolute value and norm. Maybe they put like 2 bars. I don't see the need for it. I think it's good for you to sort of get accustomed to this idea. This is certainly not universal, and it becomes cumbersome at some point. Okay, because the way I think about it is that this norm of a vector should be basically like absolute value. And then the third is very important. Namely, it relates the norm of the sum of 2 vectors to the norms of the sums. So to the sums of the norms, rather. So if I were to take v1 plus v2, look at the norm, it should be bounded from above by norm of v1 plus norm of v2. These are the 3 axioms. So this third one is what is called the triangular inequality. We're going to see a similar thing for this distance function as well. And they are related, of course. And let me perhaps mention why this is called the triangular inequality. And this is pretty much like the main tool that you're going to use to come up with estimates. So this is important. This is what is called triangular inequality. Just to give you an idea, here's a picture. Of course, this abstract vector space I can't quite draw. I don't even know if it's finite dimensional. But I can always figure out where the origin is, because any vector space has an origin. And if I'm trying to imagine things, I can just say, OK, here's the origin. And if I have 2 vectors, and this is all there is to it, this third statement is about 2 vectors only, I can just look at the plane that contains both of them, assuming that these are linearly independent, of course. So now I'm just looking at this maybe infinite dimensional vector space V, but I'm looking at that slice of it passing through the origin that contains both V1 and V2. And so here's the 0 vector. This is the origin of the vector space V. I have V1 pointing in some direction, let's say here. That's my V1. This is V2. And then, of course, I hope you know that if I'm imagining vectors to be arrows like this, emanating from the origin, vector addition just corresponds to adjoining this arrow to the end of this other arrow to get the sum. So I'm looking at this parallelogram. I just took this this vector, translated it over here, and so this is supposed to be V1 plus V2. This is the vector V1 plus V2. OK. Now, I told you that norm of a vector is supposed to be the magnitude, so the length. So that, for instance, I can look at this triangle over here. In this triangle, this side has length V1 norm. This side is just a translation of this. And I know that translating vectors should not change their magnitudes, which means that this side has length V2 in norm. And of course, the length of this is V1 plus V2 in norm. So I'm looking at this triangle over here. And so This was known since ancient Greek people. If you have a triangle like this, the sum of the lengths of two edges should always dominate the length of the other side. That's why this is called the triangular inequality. Right, so how can you see this? Well, what you can imagine is something like this. Imagine this and this both to be rods. Let's say that you have a hinge here. Okay, so let's say that you move it like this. And so you're rotating this side and it comes all the way here. And if you were to do the same thing here, okay, something like this perhaps, so that this length is the same as V1 in norm, and this length is the same thing as V2 in norm. And there's an overlap. If there were no overlap, I would not be seeing any triangle. So at best, what can happen is that they just kiss, right? In which case, V1 in norm would be V1 in norm plus V2 in norm would be exactly V1 plus V2 in norm, but certainly this would never be greater than the sum of these two. That's the whole idea. And so that's why this is called the triangular inequality. Next week, when we start talking about metrics, distances and metric spaces, basically this is all we're going to assume. We're going to forget about the vector space structure also, and we're just going to demand that this D function satisfies, it's a function that satisfies this property. So the distance between these 2 points plus these 2 points dominates the distance between these 2 points. That's all we're going to assume, essentially. There are two more sort of assumptions that we're going to have to assume, but they're less important. Let's put it that way. OK. Any questions about these? Are we going too slow, too fast? Good, OK. You say that now, but OK, so let's see. I guess I should mention a couple examples. What is the first example? Of course, if for V equals R, absolute value didn't satisfy these, there would be no justice in the world, right? So certainly the absolute value function that you use a lot in 3210 satisfies these properties, right? So the absolute value of a number is 0 if and only if the number is 0. And the product of two numbers, so the in absolute value is the product of the absolute values. And certainly this is also correct. I'm sure you have spent some time verifying this in dimension 1. Now, in dimension 2, for instance, or dimension n, so assuming V equals Rn, the standard norm is what is called the Euclidean norm. And so what I can do is I can say V in norm is going to be the sum of Vi norm squared, or absolute value squared, and then you take the 1 over, you take the square root of this. Right, so this is the so-called Euclidean norm. And so why would you look into this, or why would you consider this? Well, you know from standard geometry, basic geometry, that there's this thing called the Pythagorean theorem. And so this object basically does that, right? So if I have a vector like this, let's say in 2 dimensions, x coordinate v1, y coordinate v2, what is the magnitude of this? Well, this is a right-angled triangle. So the length of the hypotenuse is, well, the length of this squared plus the length of this squared, and then you take the square root of that sum. So this is, we're also going to call this the L2 norm, by the way. Because it turns out that there are many other norms, in fact, a whole family of norms, in such a way, such that this L2 norm is only one of the nice elements, let's say, in this family. And so the family is what is called the LP norms. There are versions of this in certain infinite dimensional spaces also, but this is what we're interested in mostly, so let's just focus on this. And so the way you define these is by looking at this expression and replacing all instances of 2 by some arbitrary number p. So let's say that p is a number that is between 1 and infinity, 1 included, at least for now, infinity not included. And then if I have v, which is an n-tuple of numbers, I define its LP norm to be like this. So I'm looking at this expression, and I'm replacing all instances of 2 by this arbitrary number p. Vi in absolute value. I see a 2 there in the exponent. I replace that by p. And then instead of taking the square root, that is to say, instead of taking the 1 over 2 power of this sum, I look at the 1 over p power of this. It's perhaps hard to believe, but indeed it turns out that this is a norm. And I think perhaps tomorrow I'll spend some time verifying this. And indeed, it turns out that you can even go further and take the limit of this expression as p goes to infinity. Okay, so this is a real number. I fix a vector. So now I have a sequence of numbers, real numbers. I know what it means for taking the, I know how to take the limit as p goes to infinity here. And so if I do that, I get what is called the L infinity norm. Limit as p goes to infinity of the LP norm of v. So this is denoted by this, v in norm with a subscript L infinity. And also it turns out, I think I'm going to leave this to you as an exercise. It's a very nice exercise. That this is a very nice expression, in fact, even though a bunch of limits and stuff are involved. It's nothing but the max of the largest component, or max of the components. Max of vi in absolute value, where I varies between 1 and n. I'm going to say more about these examples next time. But before we conclude for today, one of the things that we're going to be interested in, that's going to be very useful, is the case when the vector space you're looking at is a vector space of linear transformations. So a space of matrices. Okay. Oh, maybe I should mention this as well. If I have a vector space together with a norm on it, that is called a normed vector space. Normed space or normed vector space is a vector space V with a norm. So you have the vector space structure, addition, scalar multiplication, but on top of that, you have the ability to say this vector has this magnitude. And so let L be a linear transformation and V and W be normed spaces. The operator norm of L is defined like this. Again, I'm just going to write L in absolute value. This is supposed to be something like a norm. It's going to be the inf. This is a class in analysis, so we're going to have to use things like inf and sup. Don't worry, I'm going to remind what these mean tomorrow of all those k's, non-negative numbers, such that for any v in V, the norm of V, the norm of the image, LV, is bounded from above by k times the norm of V. This is like almost like a derivative, if you want. If you were to take this to the other side, this k is an upper bound on the rise over run. That's a good way of thinking about this, at least in the context of calculus. We're going to spend plenty of time tomorrow on this. And then I would like to discuss more these LP norms, because we're going to be using these very often in this class. OK, that's it for today. Thank you. I'll see you tomorrow. OK, let's start. Good morning. So today we're going to keep working on this operator norm defined for a linear operator between normed vector spaces, or normed spaces. And then I promised that I was going to discuss this LP norm business. We're going to do that certainly sometime this week, but maybe not today, because this is more important. And part of the reason is that the definition of the operator norm, at least the way I defined it, uses this notion of infimum, which you've studied in 3210, but I think it would be good to do a recap of this idea. So if I have two norm spaces, so these are vector spaces, and on V I have a norm, which I here denoted by absolute values sub capital V. That's the norm defined on V. That gives me a notion of magnitude, right? So lowercase v in absolute value, subscript uppercase V, means this is the magnitude of the vector V in uppercase V. And likewise, there's a norm on W. And that I denoted by this. If I take a linear transformation from V to W, I define this possibly infinite number operator norm of L. And this is how I like to denote it, L in absolute value. Some people write L in absolute value subscript op to emphasize that it's an operator norm, because it turns out that there are other norms on the space of linear transformations. Operator norms or matrix norms, in case V and W are finite dimensional, these turn out to be special. We're going to discuss what that means. This is also very common. Instead of putting one absolute value, you put two absolute values. And this sort of like says this. Or some people also use this notation. L in absolute value, and then maybe like this, from V to W. These are all sort of notations that are in the literature. Now, of course, you should immediately think that if I'm calling this the operator norm, certainly it should satisfy the axioms of a norm that we discussed. That is true. We're going to show that today. And I'm going to call an operator L a bounded linear operator if its norm is finite. It turns out that there are also operators whose norms are infinite, at least in infinite dimensional vector spaces. These turn out to be very useful, essential in quantum mechanics and stuff. We're not going to use these unbounded operators. We're going to only use bounded operators as far as I can see in this class, but still. That's why people sort of specify bounded linear operators. And I'm going to denote BL, BW to be the vector space of bounded linear operators from V to W. Of course, again, the moment you see this, you should immediately question if indeed this collection of bounded linear operators is a linear space, which means that if I were to take two linear operators that are both bounded, is it the case that their sum, which of course is a linear operator, is also bounded? And when you think about it, if you're trying to show whether or not this is bounded, certainly if you had something like triangular inequality, which would allow you to bound this guy by this, this would immediately show that the sum of two bounded operators is bounded. Now, we haven't shown that this holds for the operator norm, so we need to verify this also. You see, so once we verify this, the fact that this is a vector space is going to sort of pop up. And likewise for constant multiple of a linear operator as well. Any questions about any of this, anything here so far? Okay. Maybe even before going any further, I should try to give an example, at least in finite dimensions. Let's consider this. For instance, A, let's say that it's a linear transformation whose matrix, say in the standard basis, is the diagonal matrix 0, 3, 0, 0, 4. Now that we sort of discussed this relativity and everything is dependent on the bases and blah, 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 I'm going to sort of fast forward things a little bit, and I'm just going to give you the matrix, and I'm going to say, think of this as a linear transformation. Of course, what this means is that I'm really thinking of this guy, right? These are the same things. This is perhaps more convenient because this sort of gives you the matrix notation. Now, what you can do is this, right? You can say, oh, we have this classification theorem. A is a vector in the space of 2 by 2, in the space of linear transformations from R2 to R2, I know that this is 4-dimensional, which means that this is isomorphic to R4, which means that as the norm, maybe I want to use the Euclidean norm. And I might want to say a norm should be, well, I'm just going to look at the entries, take the squares of each of them, add them up, and then take the square root. Of course, this gives you 5. So this, maybe I should emphasize this. Let's call this norm Euclidean norm. I'm thinking of A as a 4-dimensional vector, and I'm computing this number. I can say that this is the magnitude of A. This is perfectly valid. Maybe I should ask you, do you have any contentions with this calculation? Mathematically, everything is correct, by the way. What is happening? Oh, go ahead.
I would have thought that we'd use the determinant for an operator norm based on a matrix, but this makes more sense because it is, the max it can stretch a vector is by 5 in this direction.
Well, not quite actually. The maximum expansion you see here is 4. We haven't discussed this, but if you've taken 2270, you know about eigenvalues, and eigenvalues basically tell you about, and eigenvectors, they tell you about directions along which your linear transformation sort of stretches or contracts the most or the least. In this case, if you were to think about this, 1, 0 is one eigenvector associated to the eigenvalue 3. The other one is 4. The other eigenvalue is 4. And to the eigenvalue 4, of course, the y-axis vector, 0, 1, is it's a normal eigenvector. And so if you really want to think of A as a linear transformation, perhaps instead of computing this Euclidean norm, you want to sort of come up with a norm that signifies this stretching and contracting properties of A. That is to say, you want to look at the spectral properties of A. And indeed, it turns out, if you were to compute the operator norm, using the Euclidean norm here and there, that gives you 4. More generally, if you were to do this, it would give you the top singular value, if you remember what that means. If you don't remember it, don't worry about it. And so operator norm really is about taking your linear transformation and treating it as a linear transformation. The problem in doing this is that this is an isomorphism of vector spaces. The moment you translate your language from here to there, you're losing operational structures. There's no multiplication here, matrix multiplication. There's matrix multiplication or operational structures there, you see. So that's something important. Does this kind of make sense? So in a sense, you're replacing one definition of a norm that is easier to compute but doesn't say much with something that is harder to compute but says more. So I'm going to leave this to you actually to compute. And maybe if I want to be clear, I want to say L2 to L2. Euclidean to Euclidean. Geometrically, what this is doing is that you look at the unit disk in the plane. You apply 1, 1. You apply your transformation to it. And of course, this is a diagonal matrix. It is the x-axis and the y-axis are preserved. All you're doing is that you're turning this into an ellipse where in the x-intercept will be 3 and minus 3, and the y-intercept will be 4 and minus 4. So it's going to be something like this. And then you say, oh, the operator norm of this should be the maximum stretch. That's the geometric way of thinking about this operator norm business. Okay? In arbitrary normed spaces, it's not as straightforward how to draw this transformation, but you can imagine once I have a norm, I can still talk about the unit disk, unit ball perhaps, it's better to say. We're going to sort of describe these ideas also. Does this kind of make sense? Okay. Now let's try to remember, let's try to unpack this definition. The main problem I'm sort of predicting is this inf. You've seen this in 3210, but maybe you're kind of shaky, you've forgotten about it and stuff like that. How many of you are comfortable with this inf? Okay, some of you. Okay. I predicted right because it takes a while. Now, and I would recommend that you go to my 3210 lectures and watch these. But let's try to sort of think about this. Before looking at the inf, forget about the inf. I have here a set of non-negative numbers. Okay. So let's say that I fixed my operator L. Once I fix my operator L, I have here a set of non-negative numbers. I'm going to stop writing these subscripts to be faster. This is a subset of non-negative real numbers. In particular, it's a subset of real numbers. Now, at this stage, actually, we don't know if this is empty or not. Okay. This being empty corresponds to L being unbounded, right? But in any event, let's assume that this is not the empty set. Certainly, it is bounded from below. By definition, any number here has to be non-negative. So 0 is a lower bound for this. There's an axiom about real numbers, which says that if you have a non-empty set that is bounded from below, it has an inf. This number, there's a number that you can associate to any such number, any such set. So let me perhaps write it down. Depending on your psychological makeup, this is an axiom or a theorem. I can take it to be both. That's, I think, what I did. Any non-empty set of real numbers that is bounded from below has a best lower bound. Okay? And this is called the inf. So if we were to call the set S, this would be inf of S. Now, what do I mean by best lower bound? Well, if you have a non-empty set that is bounded from below, you're saying that I have this set, and the collection of all lower bounds for the set is a non-empty set. So here's how I think described it. Let's say that this is my set. There's a bunch of things here. This is my S. Well, a lower bound is something, it's a number that is to the left of all elements in S. So this is a negative infinity direction, this is a positive infinity direction, let's say. Minus infinity, plus infinity. But maybe this lower bound, this green bound, can we all see this color? Okay. So this guy, it's a lower bound, but maybe it's not the best one. And the way I like to imagine this is that I have here this object S, and I'm trying to clamp down on it. Okay? Imagine this sort of like to be like a physical object that you're trying to sort of fix in space. There are these clamps and stuff like that when you're doing carpentry and all that you use. And so what you want to do is you want to squeeze this as close to as possible. So you keep pushing this way. And at some point, you hit the absolute best position you can get to. That means that if you were to try to squeeze it any further, you're going to start missing some of the elements. That's the infimum. It's basically the minimum, but with minimum there are certain problems that we're going to discuss in a second. This is a lower bound. If you were to try to do the same thing from the right, that gives you the sup. Okay? Same idea. You start with an upper bound. Okay, it's pretty much the same color, I guess. Sort of keep pushing, 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 and then eventually, at some point, you cannot push any further. The moment you start pushing any further, you're going to start missing some of the points in S. Okay? So this is the inf, the other one is the sup. Does this make sense? This is an intuitive way of thinking about it. Of course, when it comes to actually estimating things, we're going to have to operationalize this a little bit more. We're going to start, turning these into like epsilons and deltas, whatever. But this is sort of what I imagine always. Now, maybe I should ask you, what is the difference then between inf and min? Because as far as I'm concerned, the way I describe this makes it sound like inf is the same thing as min. What is the difference? Yeah.
Does the minimum have to be included in the set?
Exactly. So that's the thing. Okay. So if you're talking to an engineer, probably you don't want to sort of spend a lot of time saying actually, right? It's like inf, this is min doesn't exist, blah blah blah. But if you're talking to a mathematician knows the difference between inf and min. The idea is this. Maybe I should give you an example. Simplest example, of course, is an interval. Let's say that my set S is, let's say 1, 2, open. Recall this was my notation for open-ended intervals. So using the set builder notation, this means that this is the set of x's in R such that x is strictly between 1 and 2. Now, 0 is a lower bound for this. It's not the best lower bound. Then I can look at 1/2, right? 1 minus 1 over 3, 1 minus 1 over 4, blah, blah, blah. And ultimately, I get to 1. 1 is the infimum of this set. But the minimum of this set doesn't exist. You say that the minimum exists insofar as this infimum is included. Okay. Here's another example. Let's say now 1, 2, I'm including 1 and not including 2. then infimum again is 1, surprisingly. And in this case, the minimum is also 1. Okay, that's the difference. So by an axiom, infimum pretty much always exists. Whereas minimum depends on whether or not that set that you're trying to control using the lower and upper clamps contains those bounds. So to wrap up, min of S exists if and only if inf is an element in S. That's the sort of short way of, or that's a summary of this whole business. Any questions? Of course, you spend a lot of time on these infs and sups in 3210, but it takes a while to get accustomed to these ideas. And remember, I told you yesterday that this week, sort of the flavor of things are going to change a little bit. First week, we were doing just algebra stuff. Now, inf and sup and these kind of things start to come into the picture, as you see. After all, this is a class in analysis, not algebra. OK, so now that I said this, we have a couple of things to do. We need to verify that this is a norm. But even before that, perhaps, I should ask you, is this a min? Can I replace this by a min? In general, no, of course. That's the point. Not a priori, but that's a statement to be proven or disproven is the point. Let me erase this. Let me write it like this. Replace inf by min in the definition of the operator norm. In the definition. Any ideas? Now, what does that mean? Right? So using our definition, using this heuristic or summary over here, what am I really asking? I'm saying, AKA, the question is this. Is it true that LV, the vector norm, is bounded by ln norm times v in norm for any v in v? When you open up the definitions, that's what I'm asking. Certainly, in one dimensions, this is true. In fact, more is true. There's equality here. One dimensions, linear transformations are just multiplication by a number, the absolute value. And in one dimensions, vectors are just numbers as well. And so the absolute value of the product of two numbers is the product of the absolute values. That's fine. Now I'm asking about higher dimensions, and instead of saying equality, can I at least upper bound the norm of the image? It's a yes or no question, so there you have 50-50 chance. It turns out that the answer is right. So the answer is yes. So let's try to prove this. I was initially thinking of leaving this as an exercise, but as a recap of infimum and stuff and how to actually use these in proofs, let's try to prove this. This is something to be proven, okay? That's the first step to realize. And I'm asking something like this. You guess, okay, it's correct, false, whatever, and then you try to prove it. This is not an obvious statement, at least for our situation. So this is a statement I'm trying to show. For any v whatsoever, it should be the case that the norm of the image of v under L is bounded from above by the operator norm of the operator times the norm of the vector. So this is what is called the subadditivity property. Okay. The problem here, of course, is that I don't have direct access to this number. It's the inf of some crazy set. So now I need to sort of open up that definition of the inf to actually turn it into some estimates. Okay. Now, first of all, I note the following, for instance. There's a couple different ways of doing this, but the way I thought of doing is the following. The problem is not the zero vector, okay? Because if v, lowercase v, were 0, left-hand side is 0, right-hand side is 0. Of course, I need to say something, assuming that L is a bounded operator. Otherwise, it doesn't work, actually. But assuming it's a bounded operator, you can replace inf by min. So lowercase v equals 0 vector is not a problem. Left-hand side is 0, right-hand side is 0. And I hope you can see why I'm assuming that the operator bound is bounded as well, because this is how I bypass the problem of defining infinity times 0. Okay? Even from a syntactic point of view, it's, I hope, expectable or understandable why I would want a bounded operator there. But if v is 0, left-hand side is 0 and right-hand side is 0, there is nothing to do. So the problem is what happens with v non-zero. It suffices to show star, referring to this equation, for non-zero v. So let's say that I fix such a vector v. Well, in that case, what I can do is I can take this norm and send it to the other side as a division, as a ratio, right? As a denominator of a ratio. Because I know that by the definition, by one of the axioms that specifies a norm, I know that the norm of a vector is 0 if and only if the vector itself is 0. Which means that insofar as I look at non-zero vectors, I can take this to the other side. So What I want now is this. This is what I want. Now I need to open up this definition of inf, really. Look at what I was doing here and to try to come up with a more sort of functional way of understanding this inf. So what was the idea? I keep pushing this lower bound. It goes all the way here. And then if I push it any further, I'm starting to miss some of the elements. One way to sort of operationalize this is to say, for any epsilon, there is some element in S that is less than inf plus epsilon. I tried to push inf epsilon more, but now I'm missing some elements. Let me write that here. So now this is a more operational way of thinking about it. So let's say lambda, let me use a color here. Lambda is the inf of the set that is non-empty and bounded from below. If and only if two things happen. First of all, I need to have that lambda is a lower bound. So for any S in S, lambda lower bounds S. And second of all, for any epsilon, there is some S sub epsilon in S that is between lambda and lambda plus epsilon. In S, such that this was my best bound, best lower bound. I tried to push it just a little bit more, and then I started missing some elements. I'm not saying how many. I'm saying at least one. It should be the other way around. Strictly less than. Okay? This is what this means. So this is what I'm going to use. Again, by the same reasoning, I can look at the following. It's the inf of all those k's such that for any v non-zero, LV divided by v, both in norm, is bounded from above by k. And so applying the second part gives me that for any epsilon, okay, let's do this in two steps. For any epsilon, there is a k epsilon such that for any v, this happens. Such that and oh, okay, which means that if I were to connect this to this, I would have that this ratio is bounded from above by L in operator norm plus epsilon for any epsilon. For any epsilon, for any v non-zero, v divided by v and norm is bounded by this guy, which is strictly greater than L in operator norm plus epsilon. this works for any epsilon and for any non-zero e. And then if I were to take the inf over all epsilons, this strict inequality turns into a non-strict inequality, but I get this for any v. And this is what I was claiming. Any questions or comments about this? So in this step, I took the inf of this expression as epsilon, so over epsilons. Okay. Maybe you feel a little bit iffy about what I just said. There's a more concrete way of doing this. Let's remind that as well, because that's also very useful to be able to do. You can take this operational idea and in fact turn it into a sequential statement. Okay? Because I don't know about you, but this for any epsilon could be sometimes scary, at least to me. For any epsilon, any number. How do you even think about this? Well, what you can do is you can farm this statement and turn it into a sequential statement. Here's how we can do this. If for any epsilon this is supposed to happen, certainly for epsilon equals 1, it's supposed to happen also. I'm going to write it here. Oh, before going into this, what we just proved ultimately guarantees that when you're trying to bound LV, what you can do is you can split. You can just look at the separate norms. We still haven't proved that operator norm is a norm, but you can separate these sort of what are called norms, and that's going to give you an upper bound. Okay? We like upper bounds in analysis. So how to farm, let's say, double star to get a sequence? If I can get a sequence that hopefully is decreasing, then certainly I can take the limits. Then no one would have any contentions about that. So what you do is this. Choose epsilon to be 1. It's a very large error margin, but this doesn't say anything about upper bounds of this epsilon. And so there's some, technically you should say something actually, but don't worry about it. There is some s sub 1 that is strictly less than lambda plus 1. Okay, so in our picture, this is what is happening. I have here this infimum, it's the lambda. Now I look at lambda plus 1. The definition of the infimum guarantees the existence of this S1. Technically, this S1 could be equal to the infimum at this point. So that's why this side is non-strict. Either S1, this thing that you chose, happens to be in S, in which end it happens to be equal to lambda, then you're lucky and you're done. Somehow you chose one element and it turned out to be the minimum. So either S1 equals lambda, or lambda equals S1, or it's strictly greater. So X or exclusive or strictly. So not both of these can happen simultaneously. In this case, you're done. In this case, you keep going. Let's say that now epsilon is, let's say it's, let's choose epsilon to be the average of lambda and S1. So lambda plus S1 divided by 2. There are many choices here, of course. But the point is that the moment I choose epsilon to be the average of these 2 points, again, the second part over there guarantees for me that there's an S2, yet another element. Such that, and certainly, if lambda is strictly less than S1, that means that epsilon, this epsilon that I chose, is strictly less than S1. And by the definition, well, I guess depending on this statement, I should be choosing epsilon in such a way that this number is exactly this guy. But it doesn't matter, actually. So I should be saying, OK. Let's be a little bit more specific here. So what do I need to do? What I'm trying to do here is that I want to choose now my epsilon in such a way that this lambda plus epsilon is strictly less than S1. Which means that I need to choose epsilon to be less than this guy, actually. So let's choose epsilon to be this, divided by 2. OK, now it works. There's an S2 in S such that S2 is strictly less than S1 and possibly equal to lambda. And then again, you say either S2 is equal to lambda, in which case you're done. Otherwise, you keep going like this. This generates for you, by the so-called induction principle, a strictly decreasing sequence of real numbers that certainly converges to lambda. Now you can take the limits over that sequence and basically turn that turn this part of the argument into a sequential statement. And then you take the limit as n goes to infinity of this side, and then by the squeeze theorem, again you get this. Okay? Not going to write it down, but that's how you do it. Is this kind of clear? This is also one of the main tricks. You can think of infs and blah, blah, blah in these terms, or you can keep sort of choosing smaller and smaller epsilons to get a sequence. Now, in this case, it didn't matter in which speed we were converging, but sometimes perhaps you need to be more careful. Sometimes you need to choose sort of like an exponential sequence. So maybe you want to sort of decrease the error by 1/2 to the n or something. So at each iteration, you want to get one more order of magnitude, things like this. In abstract math, you get to do this. Of course, from a computational point of view, it might be more expensive, and maybe it's impossible to do this. But in abstract math, you can just estimate things however well you want, insofar as it's admissible to do this. OK. Any questions about this? This was just like a recap of inf, sup, all this stuff, how to use these ideas. As you can imagine, we're going to use these things pretty much, daily in this class. Okay. So somehow, in this situation, for bounded linear operators, the operator norm is in fact the min of that weird set. In a couple minutes, I'm not going to start proving new things, but I want to define more things, actually. It turns out that there's a dual notion. So instead of looking at instead of trying to upper bound the image, you may want to try to lower bound it, surprisingly. This leads to the idea of the operator conorm. Okay? And so the operator conorm is defined like so. I take two norm spaces V and W and a linear operator between them. At this point, possibly unbounded. Then the operator conorm of L is this. This is a bunch of different notations as well. Let's use this one. M of L is now going to be the sup of, let's say, lowercase k such that for any v in V, instead of looking at upper bounding the image, I'm going to try to lower bound it. Now, the operator norm tells you something about maximum stretch. Operator conorm tells you something about maximum shrinkage. Okay? Maximum collapse. And it turns out the ratio between the norm and conorm turns out to be an important thing too. This is called bolicity, or condition number. It's going to show up in the inverse function theorem, I think. We're going to talk about that later, but I think it's a good place to stop for today. Thank you. Okay, let's start. Good morning. So today we're going to keep working on operator norm. Yesterday I had defined also this operator conorm, and then I mentioned this bolicity. I want to discuss these. I want to give some examples, again, around these ideas, and then we're going to switch over to inner products. One of the three main sort of geometric structures that you get to define on metric spaces or other vector spaces that are somewhat interrelated. Just to recap, if I have two normed spaces V and W, and if I have a linear operator between them, I called it A this time. The operator norm is this guy. It's the infimum of all k's, such that for any V, I can bound AV, rather the norm of it, by k times the norm of the input. And so if you were to imagine, if you were to take this norm of V to the other side, here, really this k is sort of the best upper bound on the rise over run. And there are a couple different expressions for this operator norm. I was thinking of doing them, but I think I'm going to leave them to you, and you're going to see them in the second problem set. We still need to verify that this indeed is a norm. We're going to have to do that today also. Then I mentioned that instead of looking at the largest stretch, this was sort of the geometric understanding of this operator norm, you can look at the largest compression. It's sort of like the dual notion, and it is called the operator conorm, denoted typically by M of A. So you do it the other way around. And then the ratio between these two, maybe I should mention this, the operator conorm of any operator whatsoever is bounded from below by 0, of course. And this itself bounds from below operator norm, and operator norm could be a finite number or it could be infinite. Recall that we said that A is a bounded linear operator if its operator norm is finite. I'm going to give an example of a very common, let's say, linear transformation that happens to have infinite norm, actually. So it's going to be unbounded. But in any event, in this expression, if I were to take this to the other side as a division, that's a ratio, and that ratio is what is called the bolicity, or the condition number. Now, perhaps it's better to call this bolicity because condition number is really something more general. And so if you're doing applied math, this is something that you end up needing to worry quite a bit. Typically people, let's say that you have some computational task, for instance, inversion of a matrix. But of course, you're not going to do it by hand. You're going to use some sort of, you're going to use a computer or whatever. So you really need to figure out how to handle errors that you accumulate at every single step of your calculation. And so somehow, condition number, in this case, does tell you something about whether or not those errors can be managed or not. So ultimately, what you want is that this condition number is as small as possible. If possible, you want it to be actually 1. Okay? And somehow, in the context of inverse function theorem 2, where we take a differentiable function and find an inverse for it, assuming that you're trying to find the inverse near a point that is not critical, that is to say, when the derivative is not 0, somehow this value is going to show up very naturally, we're going to see, in about a month. But I'm just preparing you for it. Now, here is a warning. A bounded linear operator, that is to say, an operator whose operator norm is finite, is not necessarily a bounded function in the sense of metric spaces. Okay, so this is an unfortunate situation. But here's an example. So we haven't discussed what metric spaces are. In 3210, I did describe it. I did sort of, at least I did give the definition at the very least. We're going to spend 2 weeks, starting from next week, on metric spaces. But for now, just to give an idea, let's look at the single variable case. Well, let's say that I have a linear transformation. And I know that the norm I should think of as the absolute value here. It's a standard norm. OK. And so we had discussed how, really, in one dimension, a linear transformation is just multiplying by a number. So let's say it is a times x. A is a fixed number. In other words, this is a 1-by-1 matrix, if you want. And I know that its graph is a line passing through the origin. Let's say that a is not 0. So that it's not the flat line, something like this. Right? This is the graph. This is not a bounded function, right? It's unbounded. But it is a bounded linear operator. What is the maximum stretch? It's a. Okay, in this case, operator norm is a, in absolute value, of course. What is operator conorm? What is the maximum shrinkage? It's again a. And what is the bolicity? It's 1. So it's the best situation. You can imagine how in higher dimensions things get a little bit more complicated, right? The largest expansion is not going to be the same thing as the largest compression, and the ratio is going to really play a big role in being able to do things, even in abstract math. Okay? And so when you see this word bounded next to linear, you really want to think of this as sort of like a joint, like one phrase, bounded linear operator. You don't want to say a bounded linear operator is a linear operator that happens to be bounded as a function, even though linear operators are functions, you see. Hopefully, in this exercise, in this problem that you're going to see in problem set 2, where you investigate different ways to calculate this operator norm, you're going to sort of understand a little bit more. Perhaps a better way of thinking about it is to say that, well, an operator is bounded if and only if it takes a bounded set to a bounded set, at least for linear transformations. So one of the things we're going to do is we're going to look at what is called the unit ball centered at the origin. So you see, this function itself is not bounded, but of course, if I were to look at the image of a bounded interval, that would be bounded. So -1 to 1. If I were to look at the image of this, now this guy is bounded. So what I was kind of alluding to is that another way of computing this operator norm, for instance, is this. Sup of AV in norm such that V is in the unit ball. V is a vector whose norm is bounded by 1. Okay. This, and there's a couple more expressions similar to this. Yeah, so you're going to have to investigate all of these. Any questions about any of this so far? Okay, so here's an example of an unbounded operator. Now, the good news, first of all, is that it turns out that if V, the input space, is finite dimensional, then any linear operator is bounded. The problem is that with what we have discussed so far, I don't think one can show this, but we're going to show this next week. And so this example for the unbounded operator is going to be sort of infinite dimensional in a sense. And so here's an example. Let's look at the following situation. Let's let V to be the space of continuous functions, continuously differentiable functions defined on, let's say, the closed interval 0, 1, taking real values. So all continuously differentiable functions from the unit interval to reals. What does continuously differentiable mean? Maybe I should ask you, what does that mean? What is continuously differentiable?
It has a derivative, and its derivative is continuous.
Yeah, right. So I get to differentiate any function in the space, and when I differentiate, I still get a continuous function. For instance, sine, cosine, all of these are continuously differentiable. Well, let's define W to be just the continuous functions. Any continuously differentiable function is, of course, itself continuous because differentiability implies continuity. And so V is a vector subspace of W, if you want. But that's not going to, we're not going to use that fact. Or maybe you will. But the point is, now I want to sort of define a linear transformation that is going to turn out to be unbounded. But to do this, I cannot just leave these as they are. I need to define some sort of norm on these. So what type of a norm can I define on V or W? You have, in fact, used this norm in 3210, but maybe they didn't tell you that you were using it. So how do you, if you were to think of a continuous function, for instance, as a vector, how do you associate a notion of magnitude to it?
just take the largest point that your function hits, that should make for a norm, although I'm not sure how useful it is.
Any ideas? Yeah?
I was going to say take its distance, like normalize it.
Distance to what?
Integrate it?
You can integrate it. That's not the norm I want to use, but yeah, you can do something like that. Well, in 3210, we had, for instance, sequences of functions, and we took limits of these, right? And there were different notions of limits. There was pointwise limits, but there was also uniform limit. And somehow, the norm that I want to use in this situation is related to this uniform convergence. And so what you do is this. You take a function defined on 0, 1. That's your vector. So this picture is one vector, right? And the space looks like this. It's continuous. Now, you look at the following number. You consider this picture, this graph, and you look at the height of the rectangle that contains the whole graph. But you want to be optimal, you want to be frugal about this. You don't want to sort of like take arbitrarily large rectangles, you want to take the smallest one. Okay? So this height you define as the norm. This is what is called the uniform norm, or C0 norm. So I'm going to call the C0 norm of f to be the sup of f of x in absolute value, where x varies between 0 and 1. Okay, it turns out that this is a norm. And next week, we're going to start talking about how norms define distance functions. And once we have distance functions, we're going to be able to start talking about convergence of sequences, continuity and stuff like that. And it's going to turn out that if you were to look at the distance function induced by this norm, and if you were to look at convergence relative to that distance, that exactly coincides with uniform convergence, interestingly enough. And so I'm going to leave it to you to verify that this is a norm. We had axioms that defines what it means for a function to be a norm. I'm going to leave it to you. And I turn V and W both to be norm spaces relative to this norm. So let me continue here. Maybe I can erase the warning. So exercise. Is a norm on both V and W. Just to remind you, why would you even want to think of something like this? Because ultimately you want to sort of combine things like uniform convergence and vector space structures. That's one way to do this, looking at this norm. But then why would you even be worried about uniform convergence? That's because what you want is, you want to be able to take a sequence of functions that converges to something, but you want your notion of convergence to be so that whatever properties the functions that the functions that are in your sequence have, you want the limit have the same thing as well. So that means that, for instance, if you have a sequence of integrable functions, you want the limit function to be integrable and stuff like that too. Turns out with pointwise convergence that doesn't quite work, and probably you've spent plenty of time in 3210 looking at all of these examples and stuff. We'll look at similar examples next week probably, or maybe the week after, throughout this class probably. But for now, let me just leave it at that. I'm just norming, turning both V and W into norm spaces with this norm. Now I look at the following linear transformation. And of course, what is the most obvious one? It's the differentiation. We had talked about how differentiation is a linear transformation. Okay. Let's say D from if I were to take an F, I want my D to send it to F prime. Differentiation operator. It's a linear transformation. Okay. We had talked about that in week 1. It turns out that this is not bounded. It's an unbounded operator. Why is that? Well, I'm going to leave it to you to verify this, but the idea is this, and this is the example that I saw on Wikipedia for unbounded operators. Well, if you were to take wave functions, so for instance, for each n, let's say that f sub n is sine of 2 pi nx. So for each n is an integer, let's say. As I keep increasing n, I have wave functions that keep oscillating faster and faster. Okay. Now, what is the norm of any one of these? What is this?
Should just be 1 for all of them.
Okay. If I were to differentiate, that is to say, if I were to look at the image, now something interesting happens, right? When you differentiate this by the chain rule, this is going to turn into a cosine, and then you're going to have a factor of 2 pi n. So as n increases, f prime, or fn prime, is going to have norm that increases linearly in n. Okay. So I hope at this point you can conclude that this is not a bounded operator. It's an unbounded operator. Okay. Any questions about this? So what is the point? What is the problem here? When you differentiate one of these wave functions, you keep increasing the amplitude somehow. Because the frequency turns into amplitude, right, when you differentiate. Of course, these are all like calculations. If these are not clear, it's a good place for you to, it's a good opportunity for you to remember all of these things. Now, there are 2 things you can do with this. One thing you can do is you can just say, OK, we're done. Or you can try perturbing, right? So this was one of the sort of 4 items that I listed when we were talking about how to approach statements in 3220. You can say, OK, so everything is fine, but I don't like the fact that D is unbounded. D is differentiation. It should be a nice thing. Then you start sort of moving things around a little bit. You cannot do much with V. You cannot do much with W. you cannot change this norm, but it turns out that you can change this norm. In a sense, the C0 norm is not quite the right norm on the continuously differentiable functions. Because the pathology here is that you're not controlling the first derivative. Turns out what you can do is you can come up with a norm that is stronger, say C1 norm, that controls not only the height of the function itself, but also the slopes. This is what is called the C1 norm. Let me write it here. So if f is in C1, let's define the C1 norm of f to be the C0 norm of f plus, let's say, the C0 norm of f prime. I know that f prime exists. Turns out that this is a norm now. And relative to this norm, of course, now you're sort of bypassing this problem. Okay? So relative to the C1 norm, f sub n is not a bounded sequence, for instance. And I'll leave it to you to verify that this is a norm. And also that the d operator relative to this norm is bounded. Okay. And of course, there's nothing special about 1, right? You can do like 15, 75, whatever. You can keep sort of taking derivatives and keep adding the C0 norms. So for instance, if I wanted to look at the differentiation operator on the space of twice continuously differentiable functions, I hope you can guess that probably I should be trying to controlling the second derivative also, and so on. Okay, so that's that. Okay, any questions about this? So you see, in analysis, we have, of course, finite dimensional spaces, but we also have infinite dimensional spaces. We still want to use the formalism of linear algebra to the extent that we can. But in this problem, for instance, taking bases, whatever, they're not going to be of help. Everything is infinite dimensional. That's why I've been emphasizing this more abstract, more geometric understanding. Okay. Okay, so that's that. An example. So now I want to define certain things. Now I'm going to set aside this structure of a norm, which was this notion of the magnitude, notion of a magnitude that you get to use for vectors, and switch over to what are called inner products, where norms are about magnitudes. The way you should think about it is inner products are about angles. So it's something stronger we're going to see. So definition, let V be a vector space an inner product on V is, okay, so if I want to talk about angles, I need to be able to take two vectors and give back a number. V is a function going to denote it like this. That takes two vectors and gives back one number, satisfying certain axioms. Satisfying I'm going to continue here. Now, whatever these axioms are, they should basically abstract out the standard dot product that you're familiar with from calculus. Not the cross product, of course. In 3 dimensions, we have something called cross product. But you see, if you were to take the cross product of two vectors, you're not going to get back a number. You're going to get back a vector. That's not what I want. I want the dot product. If I were to fix a vector in the first argument, now I have a function from v to r. I want that function to be linear. Oh. I fix the first entry. Maybe I should put v1. And I leave the second entry arbitrary. Now it's a function from v to r. I want this to be linear. And likewise, if I were to fix one vector in the second input, I again want the remaining, whatever is left of the function itself, to be linear. Let me abbreviate this a little bit. So I want this function to be an element of the space of linear transformations from V to R. And again, for any V2, I want this to be a linear transformation from V to R. I'm going to give the names of what these properties are in a second. Next, what I want is, thinking of dot products, I don't want the orders to matter. OK? So no chalk. So if I were to take v1 and v2, I want the inner product of v1 and v2 to be the same thing as the inner product of v2 and v1. Then there's one more. That's 4. How to write this? Well, if this is supposed to be something like the dot product, or if it's supposed to model angles, this is perhaps hard to visualize, but at the very least, what I want is the following. If I were to plug in the same vector in both of the arguments, I want a non-negative number. And I want this expression to be 0 if and only if v itself is 0. Now, the first two properties together is abbreviated by saying that I want a bilinear function. It's not linear, but it is bilinear. If I were to fix one of the arguments, in the other argument it is linear, and so on. This next one is called symmetry property. This next one is called positive definiteness. Okay. Now somehow there are other sort of bilinear forms that you can define with different axioms perhaps. You perhaps change this, maybe you change this, and these give you different things, for instance. If you're a little bit more loose about, for instance, this fourth axiom, you get what is called the Minkowski product, which is something that, that is used in spatial relativity, to say the least. But we're not going to get there. We're not going to do that. This is the main thing that we're going to be interested in. I'm going to leave it to you to verify that indeed the standard dot product is an inner product on Rn. Dot product on Rn is an inner product. And so how do you define this? Well, you say, if I were to take x1 xn, and then y1, y2 yn, what is the inner product of this? It should be the sum of the products of the components. Okay. Okay. Now, in the definition of an inner product, maybe I should give another example or exercise. One of your colleagues actually, in fact, earlier mentioned this idea. Let's say V is the space of continuous functions defined on 0, 1, taking real values. I can define an inner product of two functions to be, well, take their product, then integrate. That's an inner product. Okay. So it has to satisfy these properties. But of course, instead of looking at V as a space of continuous functions, why not just look at the space of Riemann integrable functions? The space of Riemann integrable functions too is a vector space. And if I were to take two Riemann integrable functions, their product is also Riemann integrable. So this still makes sense for the space of Riemann integrable functions. So this is the Riemann integrable functions. Integrables. And again, this is an inner product. Not quite. Somehow there's a problem with this. Okay? So for instance, what I can do is the following. I can take f of x to be the function that is constantly 0, except at maybe 0. That is Riemann integrable. Its integral is 0. if I were to take the inner product of it with itself, that integral is going to give you 0. So somehow this positive definite property ends up failing. This is an important exercise. The main idea is that Riemann integrable functions they have some pathologies. They could have some pathologies as opposed to continuous functions. Okay? Questions or comments about any of these? Did I lose all of you? How many of you are still following? A couple. Okay. Okay, so most of you are not perhaps comfortable with some of the things I'm saying. Maybe you should ask me some stuff. I don't want to keep moving on. I don't even know where to start. What? I can't even. Yes?
Could you just quickly basically restate everything you just said about just this part of the board?
So V, if I first take it to be the space of continuous functions, sum of two continuous functions defined on the unit interval is continuous. Scalar multiple of any continuous function is continuous. That means that V, I can abbreviate all this stuff by saying that this is a vector space. And just compress all this. Now I'm taking two functions here, two vectors. Okay. Take one continuous function, another continuous function. And I'm defining this number associated to a pair of functions to be the integral of their product. The content of the exercise is to verify that this expression, this definition, does satisfy all of these properties. Okay? So for instance, let's perhaps do one of them. How do you verify the first one? So a good thing, a good sort of practice when you're trying to understand abstract math is to look at the definition and sort of substitute everything in whatever you're trying to handle. Okay, so I'm looking at this. So V1 here is the first entry. I'm fixing an F. So proof of 1 in this exercise. Fix an F in C0. And C0 means this space. Just abbreviating. This is like common. Now what do I need to do? I need to show that integrating against F is a linear transformation. So what do I need? I need two vectors, two more vectors. Say G1 and G2 in C0. What do I want? Well, I want the integral of F times G1 plus G2. I want this to be equal to this. Of course, this is correct. You know this from 3210. What you don't know is that you know it. Okay, so I'm sort of upgrading the formalism. In a more complicated context, you may want to call, for instance, this F an integral kernel. So for instance, if you're taking Laplace transform and stuff like that, basically the same idea holds, or Fourier transform. So this linear algebra stuff it's a double-edged sword. It's like everything becomes very pristine, axiomatic, just use definitions and makes the topic very clear, but at the same time it becomes hard to sort of translate all this abstract stuff into things that you know. Okay, a big part of this class is going to be you sort of like doing this transition between abstract stuff and here's a very specific situation. Does this kind of make sense? Are we all happy with this verification? Kind of, okay.
So you explained inner product is one way to describe it is like an angle. How does that make sense for functions?
Okay, instead of talking about arbitrary angles, if I were to say something like in an inner product space, vector space together with an inner product, if I were to say two vectors are orthogonal if and only if the inner product is 0, probably that would make a little bit more sense.
Yeah.
But then you say, oh, I have all of these sines and cosines, and it turns out that if I were to look at two sine functions, for instance, with different frequencies, their inner product turns out to be 0. I mean, this is something that you compute. You use the double angle formulas, whatever. Maybe I'll give that to you as an exercise eventually. But if you were to take a differential equations class, whatever, where you sort of take a function, split it into wave functions and stuff, this is something that you use quite often. So for instance, another thing I can say is that if I were to take an even function and an odd function, in this case it doesn't quite make sense, but a sine function, for instance, is an odd function. Even cosine is an even function. Any odd function is orthogonal to an even. Any odd function is orthogonal to an even function, and so on. There's a bunch of things. Like this keeps going. It's like there's no end to this. But this definition for now is sufficient. Let v1, v2 be two vectors, v be an inner product space. And I'm going to call v1 and v2 orthogonal if their inner product is 0. Orthogonal is the same thing as perpendicular. If okay. Another way to make sense of this angle business in the case of functions is to say the following, is to sort of use the following heuristic. Well, what you can do is the following. Instead of thinking of your independent variable to be continuous, right? It's not discrete. You can say this is basically like an idealized version. Forget about having a function, having a continuous function. Don't worry about continuity also. Let's say that you have a discrete signal. Let's say 1, 2, 3, 4. If your independent variable is discrete, maybe this one is going down, this is how a function looks like. Okay? So from, let's say, you can use integers, but if you want to keep this as 1, you would just normalize, right? So you would say 1, 2, 3, 4. So this would be 1 over 5, 2 over 5, 3 over 5, 4 over 5, and so on. It could work the other way around too. Maybe your signal is continuous, but you're using a digital thing. You're sampling things. Could work either way. But so you see, this means that a discrete signal like this is determined completely by 1, 2, 3, 4, 5, 6 numbers. So this discrete signal you can think of to be an element in R to the 6, up to isomorphism, whatever. But if this is a 6-dimensional vector, I can take yet another signal. And of course, the dot product of these two should say something about the angles. OK, are we happy so far? But then let's say that you keep adding more sampling points. In the limits, ideally, you're getting the whole function that is defined. You're getting the whole signal. And somehow, the limiting procedure here should translate in the context of inner products as well. But of course, you know that this Riemann integration is basically formalizing this limiting procedure. Right? So you say, OK, so how do you even define this Riemann integral? You say, I have a signal, and I'm sort of like partitioning the input space. And I keep partitioning into smaller and smaller sort of segments. Whatever that limits, insofar as it exists, is the integral, you say. That's how we define it. And then in 3210, of course, you show that any continuous function is Riemann integrable, so that this makes sense.
It literally is a dot product.
Yes.
If you just do a Riemann integral.
Yes.
Oh.
OK. Math is just like real life magic somehow. Smart people sort of wanted to do things, and they figured out ways to do it. OK? Now, understanding that it works is a different matter, of course. And this class is all about that. OK, I think it's a good place to stop today. Thank you. OK, let's start. Good morning. Problem set 1 is due tonight. And problem set 2, it's almost ready. It's going to be up later today. So this is going to be probably our last class where we only talk about vector spaces, norm spaces, these kind of things. We have 2 things that are very important that we need to cover. One of them is this. I've been saying this. We've been using this operator norm. We've been calling it a norm, but I forgot to prove it last time. And so I started talking about inner products. So first I want to cover this, and then I want to cover a very important inequality for inner products. It is what is called the Cauchy-Schwarz Inequality. Another thing I had promised was verifying that these LP norms are indeed norms. So probably we're not going to cover this, at least for now. Maybe if we have time, we can go back to it. Because ultimately, it turns out that somehow there are certain, it's not very sort of fast to cover them. So I need to sort of do a couple of inequalities and stuff like that. And I thought it's maybe not very thematic. And ultimately, it's not a major problem if you just assume that they are indeed norms and move on like that. Before I start discussing this operator norm business again, do we have any questions? OK. So if I have V and W, 2 norm spaces, we had discussed how I can take a linear transformation from V to W and come up with this number, or extended number, let's say, called operator norm. And so for now, what we had was the following. Let's write it like this. In general, the operator norm, we said, of some linear transformation could be infinity. And then we said, well, the collection of transformations whose operator norm is finite, that is to say, the collection of bounded linear operators, is a vector space. And then we said how the fact that, or the statement that this is a vector space depends on sort of like the norm properties of this. And so we need to sort of verify certain equations. So let's write them down. Want 3 things. First of all, what do I need? I need that an operator norm, so an operator is the zero operator. That is to say, it's the operator that takes any vector whatsoever to the zero vector in W, if and only if its operator norm is 0. That's the first item we need to verify. Second, well, the operator norm of some constant multiple of an operator should be, well, absolute value of C times the operator norm of A. Maybe I should write it like this. For any operator A, this has to hold. For any operator A and for any constant C, for any scalar C, this has to hold. And then the third one was what? Maybe I should ask you. We had this third property that was very important. If you want, these are sort of technical things, but the third one is really what makes the notion of a norm a geometric thing. We need something very important.
It should be the triangular inequality.
Right? So you want to be able to bound the norm of the sum of two operators by the sum of norms. Okay? These are the three things we want. Okay. Let's start with the first one. So these are the things we want. It's an if and only if, right? So I need to prove either way. If A is the zero operator, that's the easier side. So going this direction, if A is the zero operator, that means that for any V, A times V is 0. Now A times V, or A applied to V, is a vector in W. And I know that W is a norm space, which means that for any V, 0 is also the norm of A times V. Okay? If that is the case, certainly, thus, for any epsilon positive and for any V, I have that AV, which has norm 0, is bounded from above by epsilon times V in norm, because this is a non-negative number, after all. This is trivially true. But what does that mean? If for any epsilon this holds, well, I can take infimum over all epsilons, and that gives me the definition of the operator norm. By taking inf over epsilons, let's say. Let's write it like this. Actually, thus for any n and for any v, the norm of A times v is bounded from above by 1 over n times v in norm, taking the limit as n goes to infinity. By the squeeze theorem, the operator norm has to be 0. How are we feeling about this? Now, this is a class in analysis, and we're going to keep, doing arguments like this throughout the class. This is a simple instance of that. So this is one side. How do I go the other way around? Now, I'm assuming that I have an operator whose norm is 1. Then I want to conclude that the operator itself is the zero operator, really. So in this direction, say 0 is the operator norm of A, which is inf over k's, such that for any v, AV in norm is bounded from above by k times v in norm. Right? That was the definition. OK, so I have a set of numbers. I'm saying the inf of that set is 0. OK, that means that by this farming procedure that we discussed, I can think of the following. I can say that there's a sequence of k's, k1, k2, k3, that decreases strictly to 0, that converges to 0. And that satisfies this inequality for any v. By the definition of infimum, there is k1, k2, k3, dot, 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 such that k bullet, the sequence, converges to 0. Right? Just because you have a decreasing sequence of numbers doesn't mean that it has to converge to 0. But I'm saying, let's say that it converges to 0. I get to do this because the infimum is 0, such that for any n and for any v, AV is bounded from above by this guy. If you have two for alls, you can flip the order of these. So instead of writing for any n and for any v, you can write for any v and for any n. Then you take the limit as n goes to infinity to realize that for any v, the norm of a times v has to be 0. If for any v, the norm of a times v is 0, again, this is the norm in W. Well, the only vector that has 0 norm in W is the 0 vector. That means that for any v, a times v is 0. That is the definition of what it means A to be the linear 0 transformation. Questions, comments? Yes.
I haven't seen that notation for a cable converging to 0 before.
Yeah.
It's kind of neat.
Yeah. Some people do this. Some people do sort of like diagonal, whatever. Now, when people start drawing things like this, then it starts getting complicated. And this it goes down. Okay. Yeah. So this bullet notation we're going to start talking about next week. This is my notation for sequences. The reason why is that I'm thinking of this n as my time. And when I'm writing this, instead of writing limit of k sub n as n goes to infinity, I don't call the independent variable anything. Because from 30 to 10, for instance, you probably have dealt with a lot of subsequences and subsequences of subsequences of subsequences and so on. I sort of like bypass all of that by just keeping things more closed in a sense. We'll talk about this later. But the point is that these kn's, k sub n's, they decrease to 0. I get to choose k sub n as small as I want, which means that the right-hand side is as small as I want, which means that the left-hand side has to be bounded by any positive number. And the only number that is bounded from above by any positive number is the 0 number, of course. OK? That's the first part. Second part, surprisingly, it's easier. Maybe not surprisingly. I realize I use the word surprisingly or paradoxically too often. I'm not that surprised, actually, but yeah. OK. So part 2, what do we need to do? Two things, right? So left-hand side is bounded from above by the right-hand side and vice versa. That's how you show the equality of two numbers, at least in analysis. Right? In algebra, you compute things, and then either left-hand side is equal to right-hand side or not. In analysis, what you try doing is you split the equality into two parts, show that the left-hand side is less than or equal to right-hand side, and vice versa. That's the only way two things are equal. Now, first of all, I can get rid of the case when c is 0 right from the get-go, because I know that if c is 0, the left-hand side, c times a, is a 0 transformation. And we showed in the first part that the zero transformation has norm 0. I mean, yes, it is. And so the left-hand side will be 0. And likewise, if c were 0, this is some number that I'm multiplying by 0. Again, it's going to be 0, which means that if c is 0, this is already satisfied. So it suffices to show equality for c non-zero. But the moment you realize that, you also realize that there is some symmetry going on there, which means that instead of showing either sides, you can say if I can show one side, the other side is pretty much the same thing, because, you know, instead of multiplying by c, I can imagine multiplying by 1 over c. There's some symmetry there. OK. And so let's try to do this. Writing this out can be somewhat confusing. But if you follow the definitions and if you're careful with unpacking the definitions, it's going to be fine. So I look at the definition of, let's say, operator norm of c times a. C times a is some operator. It is an operator norm. And this is some number that is given to me. Let's say that I'm sort of trying to upper bound this. And so left-hand side is by definition inf over case such that for any v, CA, this was my operator, so I need to apply this, OK? CAV in norm is bounded from above by k times b. OK. And I know that this set is non-zero, non-empty, because, well, maybe I should be starting from here, actually. Probably it's more formal to start with the right-hand side. Because at this point, all I know is that A is a bounded operator, not necessarily C times A. So maybe I should start with this. I know that A is a bounded operator, and C is a non-zero number. By definition, that means that this is this. This is a finite number, OK? At the very least, there is at least one k that is in here. Otherwise, this set would be empty. So there is a k such that for any v, A times v is bounded by this guy. For some number k, I have this inequality that works for any vector whatsoever. OK. But then, for any v, the operator C times A applied to v in norm, OK? Now I can do things, right? By the assumption that this is a norm in W, and because it's a constant, I can take this out. And then combining this with this, I have this. But then if you think about it, that means that, and k is non-negative, of course, because of this. If k is non-negative, this guy is positive, which means that C in absolute value times K2 is a non-negative number that I get to use for any V to upper bound the image of the vector under this new operator C times A. That means that C in absolute value times K is in this set for CA operator norm. That is to say, the operator norm of CA is bounded from above by this. This is an upper bound for C times A in operator norm. But to get the operator norm itself, I need to take the optimal bound. That's why this is the case. But then if I were to optimize over K's, the optimum such K is going to be the operator norm of A, which means that this is going to give me this. Again, if you're not very comfortable with this, so optimizing this and blah, 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 just turn it into a sequence and take the limits, like I did over here. They are actually equivalent by the Archimedean principle, if you want. Right? So given any two number, any two real numbers, there's one that is between them and stuff. Does this make sense? Okay. The other side I'm going to leave to you. So I showed this side. Now you need to show that this is bounded from below by this number. And now that you show this, you know that this is a finite number too, by the way. So let me write it here. Exercise. The other side. OK. Third part is the triangular inequality. And this is the most important thing, in my estimation. If I have two operators, A and B, that are both bounded, that means that if I were to look at this set, for instance, I know that it contains at least one K. And likewise, the same set for B contains some other number, K prime, let's say. So, or maybe I should use some other letters. Since both of these operators are bounded, there are numbers, let's say alpha and beta, such that for any V, AV in norm is bounded from above by alpha times B, and BV in norm is bounded from above by beta times V in norm. And what I'm trying to bound is A plus V applied to V in norm. And I'm trying to bound this guy. Then this, I add the two operators A plus B, A and B. That gives me yet another operator. I apply that added operator to V. But of course, I can just expand this and stuff. But then this is the norm in W. And I know that by one of the axioms of a norm, I can split this. And now I have this. But then this I can bound by alpha times V norm, and this by beta times V norm. Of course, you can combine these again to give you this, which tells you that the operator norm of A plus B is bounded from above by alpha plus beta. Optimize over alpha and beta, and this turns it into the operator norm of A, this turns into the operator norm of B. And that's the end. Therefore, operator norm is a norm on the collection of all bounded linear operators. And consequently, you see it kind of works the other way around. Consequently, the collection of bounded linear operators is a vector space that is normed by the operator norm. This is something that you do in analysis very often. You first take your vector space, it's something, and then you define something like a norm on it, maybe the operator norm. You verify everything, and the only problem is that there are some vectors whose norms are infinite. You get rid of those vectors, now you have a norm space. That's what you do. Okay? You get rid of vectors that are of infinite magnitude. You don't have to actually, but this is like one thing that people do often. Any questions or comments about any of this? Now you see another thing is that my notation is it's a double-edged sword. Now if you want to be more sort of proper, what you want to do is probably, for instance, in this expression, you want to note that, oh, this is not the same thing as this, for instance. It's the norm in W. You would put a subscript there to keep track. Now, this norm is not the same thing as this, OK? It's the norm in V. And this is yet another thing. This is the operator norm. So that's a different absolute value. If you want. This is the same thing as this. If you're getting confused, it's good to take a second, write things more explicitly. But then, of course, it's going to take longer for you to write things down. Initially, I wasn't that comfortable with just using absolute values or whatever. I was sort of like keep track of what is happening where. But eventually, it's like you get used to that. You get used to this idea. And I would recommend that you get comfortable with this as well. Because in the literature, most people don't write sort of like the subscripts and stuff. And they would just assume that you would understand what is happening or whatever means from context, ultimately. So if you want to think about it this way, so you can sort of imagine, like there's Python and C, perhaps. One of them is a higher order language, and Python sort of understands what you mean more often than C does, right? With C, you have to be a little bit more careful. You have to fix every type and whatever. Python, you don't need to be that careful, in a sense. So I'm using, if I don't write the subscripts and stuff, I'm using a higher order language, if you want. You can think of it that way. It's faster for many things, but sometimes it's better to go back to the basics, get closer to the assembly code or whatever. Okay? Questions or comments? Okay, now let's look into this very important inequality for inner products. Remember, last time we had defined inner products. So this was about norms, magnitudes. Inner products, I told you, is about angles. And in fact, this inequality is going to give us why one can think of inner products as angles also. In the textbook, this is called the Cauchy-Schwarz Inequality, but it's also called by some people, by Wikipedia, other places, Cauchy-Bunyakovsky-Schwarz, because Cauchy came up with this idea, came up with inequality, and then Bunyakovsky, I think he was a Soviet mathematician or something, came up, figured it out in a different context, and then Schwarz sort of proved it again, in a sense. Inequality. This is very important, perhaps more important than operator norms, at least for this class, not in general probably. But if I have an inner product space, I want to upper bound the inner product of two vectors by something. Then for any two vectors v1 and v2, maybe I should ask you, some of you might remember this. What does the Cauchy-Schwarz say? You've definitely covered this in calculus. Okay. If what you learned in calculus is correct, this is actually backwards, but heuristically, you know that the dot product of two vectors is equal to the product of the norms up to an angle. So from Calc III, you know that x dot y is x norm, y norm, times cosine the angle between. This cosine is between -1 and 1, which means that if you were to not write this, this would increase. Right? In fact, this has nothing to do with this specific dot product. It is true for any inner product whatsoever. We still don't have this angle, but we're going to get there in a second. So v1, v2 inner product is bounded from above by v1, v1 inner product. So I'm taking the inner product of v1 with itself and then taking the square root. I know that I can take the square root because one of the axioms for the inner product was that if I were to take the inner product of a vector with itself, that's going to be a non-negative number. So this always makes sense. There's no sort of funny business happening or complex numbers, whatever. Times this. That's the first part. And in fact, immediately as an exercise, I'm going to give you the following. Equality holds if and only if v2 is proportional to v1. In other words, they are linearly dependent. This is very good. And in fact, if you think about the proof that I'm going to write in a second, you're going to be able to see how we can get this. Equality in Cauchy-Bunyakovsky-Schwarz if and only if v1, v2 linearly dependent. OK. So how to prove this? I'm going to follow the, so this has like 5 billion different proofs, but I'm going to follow the one given in the textbook. It's a funny one, I think. You take your V1 and V2, and you look at essentially an arbitrary linear combination of them. And then you'll sort of take that linear combination and take the inner product of that vector by itself. That is to say, you do the following. Consider for any t, p of t defined by v1 plus t, v2, inner product with itself. So that's a function, that's a scalar, that's a single variable, real valued function if you want. It depends only on a scalar. v1 and v2 are fixed, and the outcome is going to be the outcome of the inner product, but we know that inner products are scalar valued. Okay? But in fact, I can say more. First of all, this is always non-negative by the definition of the inner product. I'm taking one vector and hitting it against itself. That's going to be a non-negative number by the assumption, by the fourth assumption of positive definiteness. For any t, p of t is non-negative. But furthermore, p of t, in fact, is a polynomial in t. That's why I called it p of t. Indeed, I can just open this up. I had these linearity properties. Right? So I said, given any vector in the first entry, this inner product is linear in the second entry. So I can split these and take this constant out. And likewise, I can do the same thing in the first one. I'm going to do this explicitly for once. By bilinearity, P of t is the following. Let's do this step by step. So now, first I'm going to fix the second entry and use the linearity in the first entry. Okay. For fixed t, the second vector here is fixed. And so if I fix this entry, in this entry, my inner product should be linear by assumption. So I get to do this. This is an important aspect. The point, of course, is that I can do the same thing again. This is fixed. Now I can distribute these. This is fixed. I can distribute these. I open this up, plus t v2, comma, v1, plus t squared. I had one t, another t coming from here. By symmetry, I can go even further because I know that this inner product has to be the same as this inner product. So collecting everything, I have this. So for fixed v1 and v2, as you see, if I'm thinking of this as a function of t, this is a polynomial of degree 2. Okay. So let's call this number, let's call it A. This number, let's call it B. This number, let's call it C. So I stored these complicated expressions into A, B, C. These are 3 numbers now. Okay, this was what we were trying to prove. I'm going to delete this. Now, what is the next step? What do I have? I have 2 things. I have one polynomial of degree 2, and I know that it's always non-negative. What can I say about its coefficients? What are the roots of this polynomial? There's a formula. It involves the square root. Inside the square root, what do I see? B squared minus 4ac, right? So this is a polynomial. I'm saying that this cannot happen. It can be at most tangent to the origin, to the 0 height, which means that b squared minus 4ac, this so-called discriminant, has to be this way. If it were positive, it would be going down, right? Do we remember this stuff from college algebra? Okay. And so we have this. And so the funny thing is that, of course, once you put everything back together, this is going to give you the Cauchy-Schwarz Inequality inequality. So b squared is, as you see, 4 times v1, v2 inner product squared. So and on this other side, I have 4 times a was v2 against itself, c was v1 against itself. I can cancel these out, take the square roots. These are these are non-negative numbers. It's fine. And I'm going to take here the absolute value. Even so, if I didn't write the absolute value there in the Cauchy-Schwarz, you should probably write it there. Might have missed it. Right? That's the left-hand side. On the right-hand side, I have that was the claim. Now really, let's go back to this exercise. I told you that equality holds if and only if v1 and v2 are linearly dependent. Now note that, what does it mean for equality? Going back, it means that b squared minus 4ac equals 0. That means that you have repeated roots. Okay, follow up from there. It's going to give you that scalar that you need in the linear combination. Okay. So that's that. And then next up is that instead of writing it like this, take the vector, take the inner product against itself, and then take the square root. Well, you might as well just think of this as a function of one vector. And so that leads to a norm. But maybe even before that, I should do this. So that was the end of the proof. Now that we know that for any v1 and v2, let's say that these are non-zero. Cauchy-Schwarz doesn't require that these vectors are zero or non-zero. But let's just look at the non-zero case. Then, of course, I have the following. The inner product of v1 and v2 is bounded from above by the absolute value of this number. Could be negative. But if I take the absolute value of this, it's going to certainly not decrease. So I have this bound. But then by the Cauchy-Bunyakovsky, I have this. And by my assumption that v1 and v2 are non-zero vectors, neither this nor this is a zero vector, a zero number, which means that I can take them to the other side as a division to look at the ratio. v1 against v2 divided by v1 norm times v2 norm. That's a number that is strict, that is between -1 and 1. Okay, so because if I take this to the other side, I'm going to continue from there. So if given any two non-zero vectors, this quantity is a quantity between -1 and 1. That means that there is a unique number between 0 and 2 pi whose cosine is this. Because cosine from 0 to 2 pi goes from +1 to -1. It's not unique, actually. Probably I should say 0 to pi. Now it's unique. Otherwise, there will be two numbers. But then if that is the case, well, I can just define this theta to be the angle between v1 and v2. Okay? So that's how we define the angle. And I'm going to leave it to you to verify that indeed what we defined last time as orthogonality, perpendicularity, matches with this. So the angle between two vectors is 90 pi over 2 if and only if they're orthogonal. So this does allow you to actually talk about angles. Even if this inner product was this integration, okay, so that means that you can take two graphs of functions and compute the angle between two graphs somehow. Not at one point, but you take the whole graph. It's a holistic idea. You take the whole picture. You take another picture. You sort of combine them together using this integral. It gives you one number. Just by looking at that number, essentially, you can compute the angle. Okay? I hope you're starting to get convinced why linear algebra is this powerful. Okay, comments, questions? I want to say one final thing. Namely that this expression then defines a norm. Exercise. On V. So whenever you have an inner product, you also have a norm defined like this. So any inner product space is also a norm space, but not necessarily vice versa, it turns out. OK. I think that's a good place to stop. Thank you. Have a nice long weekend. We don't have class on Monday, but we're going to be back on Tuesday.